A very good morning to all of you. I welcome you all for this engineering thermodynamics course. So today's classroom discussion topic is numerical problems on Otto cycle, air standard efficiency and mean effective pressure. So the motivation for this today's class is it is important to predict the performance of an Otto cycle. That is, whenever a petrol engine is working, so definitely we have to find out what is the air standard efficiency and mean effective pressure of that particular the petrol engine. So the outcome of the today's class is to solve numerical problems on Otto cycle. So in the previous class we discussed about the Otto cycle working principle and the PV diagram and the TS diagram of the Otto cycle. That is, it is basically containing two reversible adiabatic process and two constant volume process. So constant volume heat addition and constant volume heat rejection is taking place in the Otto cycle, and similarly isentropic expansion and isentropic compression process is taking place. So two reversible adiabatic and two constant volume processes are taking place in this particular the Otto cycle. And similarly we studied that the total volume is equivalent to swept volume plus is the clearance volume. So with this basic input about the Otto cycle, and we also studied that efficiency of the Otto cycle is equivalent to 1 minus 1 by R to the power of gamma minus 1, where R is equivalent to the compression ratio, that is equivalent to V1 by V2. And normally in the modern SI engines, the compression ratio is limited to the 12. And if the compression ratio exceeds 12, then automatically the knocking problems we are able to experience from the petrol engine. So to avoid the knocking problems or the detonation problems, we are restricting the compression ratio only up to 10 to 12 in case of the petrol engines. So with this particular input, in the today's class, we will solve some problems based on Otto cycle. So this is also one of the problem which is given in the previous GATE examination. The efficiency of an Otto cycle is the 60% and the gamma adiabatic index is equivalent to 1.5. What is the compression ratio? So if you want to answer this particular question, so that is basically you should know the efficiency of Otto cycle. That is efficiency, you know that 1 minus 1 by R to the power of gamma minus 1. That is the air standard efficiency of the Otto cycle. Now first you write down the given data. So he has given the efficiency is equal to 60%, that is a 0.6, and the gamma value is given as a 1.5. Simply is asking about R. So if you know this particular fundamental equation of Otto cycle efficiency, then you simply substitute the values. So then we are able to get R. R is nothing but the compression ratio. So that will be equivalent to 6.25. So that is the answer for this particular question. Next, let us see the another problem. So this problem was appeared in GATE 1998. So the minimum pressure and temperature in an Otto cycle are 100 kilopascals and 27 degrees centigrade. So just you see the PV diagram of the Otto cycle here. So he is saying that is a minimum pressure and temperature. So whenever you are going through this particular PV diagram, you are able to have the minimum pressure only at this particular point number 1. So at the point number 1, it is giving you P1, and here it is the P2, and it is a P3, and it is a P4. So that is minimum pressure is at the P1, and the maximum pressure and temperature you are able to observe at point number 3. So minimum pressure, so that's why here he has written P1 is equivalent to 100 kilopascals. So always you convert into the SI units, that is a Newton per meter square. So 10 to the power of 5 Newton per meter square. And a temperature 27 degrees centigrade, always you have to convert into the absolute temperature. So 27 degrees centigrade is nothing but 300 Kelvin. So the amount of heat added to the air per cycle is 1500 kilojoules per kg. Amount of heat added, because I already told you that heat addition always takes place according to the constant volume process in the Otto cycle. So that is during the process 2 to 3 only the heat addition will take place. So Q2 to 3 value is given as 1500 kilojoules per kg, and the compression ratio value he has given as 8:1. So it is a V1 by V2, that is the V1 by V2 value is given as 8:1, and for air always these are the standard values. Specific heat at constant value 0.72 kilojoules per kg Kelvin. Actually here Kelvin is missing, but air is there, and gamma is equivalent to 1.4. So now he is asking that Determine the pressure and temperature at all points of air standard Otto cycle. So pressure and temperature at all points. So that is, he has given only P1, T1. Now he is asking about P2, T2, P3, T3 and P4, T4. And what the second bit is also asking us to calculate the specific work and thermal efficiency of the cycle. So how to proceed? So always PVT relationships are very important one, because the expansion and compression processes are taking place according to the adiabatic process. So just you recall the PVT relationships. Now this is the volume and temperature relationship in case of the adiabatic process. So T2 by T1 is equivalent to V1 by V2 whole to the power of gamma minus 1. So from which we are able to estimate T2 is equivalent to 689.1 Kelvin. And we know that the basic governing equation in the adiabatic process is P1 V1 to the power of gamma is equivalent to P2 V to the power of gamma. So from which we are able to estimate the P2 value also as 18.379 bar. So next one is the constant volume process, because you know that during the constant volume process the heat transfer is equivalent to Cv into delta T. So we know the heat addition is equivalent to 1500 kilojoules per kg. So find out the temperature, that is the peak temperature or the maximum temperature in that particular the cycle as 2772.4 Kelvin, and the maximum pressure is equivalent to 73.94 bar. And similarly you consider the 3 to 4, that is the reversible adiabatic expansion process, by using the volume and temperature relationships. Find out T4 is equivalent to 1206.9 Kelvin, and by using the basic governing equation of the adiabatic process, P4 is equivalent to 4.023 bar. And the second bit is asking about the specific work and thermal efficiency. And we know that work is nothing but is a heat added minus heat rejected. So Cv into T3 minus T2 minus Cv into T4 minus T1. So you know all the values, substitute. We will get the specific work output by this particular the Otto cycle. It is equivalent to 847 kilojoules per kg. And similarly, the last one is the thermal efficiency. So you know that 1 minus 1 by R to the power of gamma minus 1. It is a formula to estimate the A standard efficiency of the Otto cycle. And he has clearly given the compression ratio is equivalent to 8:1. So that is 8. And the gamma value also clearly given. So substituting all the values, we are able to get the thermal efficiency of the Otto cycle is equivalent to 56.47%. So similarly, let us see the another problem based on the Otto cycle. So an engine of 250 mm bore, so that is a diameter. So bore is nothing but a diameter. So diameter he has given as 250 mm and 375 mm stroke. That is the length of the stroke he has given as the 375. So just you see here, length of the stroke, it is a L is equivalent to 375 mm, because the bore and stroke are given in the mm. So convert into the SI units, it is the meters. And similarly the clearance value, so VC, so this is the clearance value. So clearance value is given as 0.00263 meter cube. The initial pressure and temperature values are given, that is the 1 bar and 50 degrees centigrade P1 and T1 convert into the Kelvin temperature. So now he is asking about the air standard efficiency and mean effective pressure of the cycle. So that is the basic today's discussion topic. So with this particular one, so the basic equation to find out the Otto cycle efficiency is 1 minus 1 by R to the power of gamma minus 1. So we don't know the compression ratio value. So instead of giving directly the compression ratio value, so he has given the length of the stroke and similarly the bore. So with this particular bore and stroke, how can we find out the compression ratio? So that is the swept value. The swept value is always is a cross-sectional area into length. So the cross-sectional area is nothing but pi by 4 d square into length. So we know the bore, so 0.25 meters square, and L length of the stroke 0.375. So the swept value we can find out as 0.0184 meter cube. And in the problem he has given the clearance value. So when the swept value and the clearance value are known to you, then how can we find out the compression ratio? So the compression ratio is nothing but is the total volume divided by the clearance value. That is the formula to find out the compression ratio. So the total volume is nothing but the swept volume plus clearance value. So we know all the values. So by substituting that, we are able to find out the compression ratio is equivalent to 8. And by substituting this, we are able to find out the air standard efficiency is equivalent to 56.5%. And next one is the mean effective pressure. We know the basic formula, that is the work done divided by the swept value. So you know the work done and you know the swept value, so that the mean effective pressure is find out as 1.334 bar. So in the today's class we solved some problems based upon the Otto cycle, air standard efficiency, and mean effective pressure. So thank you all for listening this lecture on the Otto cycle numerical problems. Thank you.